My name is Ignacio Galindo, and this is my Physics 2211 Lab 4 Oscillations. There's some goals for this lab to begin with. First, we need to compare the predicted motion with the observed motion of a mass attached to a spring, and then we need to plot the energy changes that occur in the system for the predicted motion. These include the change in kinetic energy, the change in gravitational potential energy, the change in spring potential energy, and the change in total energy. After conducting the experiments, I found that the predicted motion and the observed motion are similar in the x and y axes, but there's more similarities within the x motions. The change in total energy is also zero, and the changes in the other energies reflect this, which I will discuss. Some of the key concepts for this lab are Newton's second law, which include the equations such as F net equals delta p over delta t, and the velocity update, which is velocity initial plus F net over m delta t, as well as the position update formula, which is Ri plus b average delta t. We also have to take into account the energy principle, which states that delta E sys is equal to the work done by the surroundings plus any energy transferred through heat. Also, the kinetic energy is 1/2 mv squared, or the translational kinetic energy, but the potential energy is mgy, and the spring potential energy is 1/2 ks squared. For this lab, we set the system to be the Earth, the spring, and the mass, and the surroundings to be nothing. And so since we are setting the system to include all elements that do work on the mass, then nothing in the surrounding actually does work. So W sir is equal to 0, Q is equal to 0, and therefore delta E sys is equal to 0. Given this relationship, we can say that delta E sys is equal to the change in kinetic energy plus the change in the gravitational potential energy plus the change in the spring potential energy. We can also observe a free body diagram which displays the static equilibrium position of our experiment, where Fg is equal to the magnitude of the spring force. So F net is equal to 0, which is also equal to Fg plus Fs, and in vector form, F net is equal to negative mg in the y direction, while the spring force is equal to Ks in the positive y direction. Tracker was used to track the motion of the spring. So this analysis included a video which was set to 10.5 frames per second, so 0.095 seconds per frame. The object mass was 0.402 kilograms, and I observed that the start time obviously was at 0 seconds. The initial position was negative 0.104 in the x axis and negative 0.643 in the y axis. The initial velocity was 0, and the last observation was at 9.497 seconds. For the computational model, we started with initial conditions mentioned in the last slide, with the mass being 0.4, the position being negative 0.1 in the x direction and negative 0.6 in the y direction, the velocity being 0, and also delta t being 0.095 because of the frames per second or seconds per frame. Here, g is 9.8. The spring constant is at 6.83, which is found from the period of oscillation and the formula for k. The lag setting is 0.123 as indicated. L hat, and S are all calculated using their respective formulas, and all the energies are also calculated using their respective formulas. Also, total energy is 0, as mentioned before. In the calculation loop, we iterate till 9.497 seconds, because that is how long the tracker analysis goes for. We define the initial energies, the initial forces. We update velocity and position with Newton's second law. We also update L hat, and S, and we calculate the energy changes as well. Also, E and delta E are 0, as also mentioned before. As we can see from the results, the change in potential energy is kind of a reflection across the x-axis of the change in potential energy of the spring. So they have opposite signs, and delta K is very small compared to these two. You can also see that delta E is 0 the whole time, as we mentioned before. We can also observe that the predicted motion and the observed motion are very similar in the x position versus time graph, while in the y position versus time, the model analysis and the experiment analysis differ more. The change in gravitational potential energy and change in spring potential energy oscillate, while the change in kinetic energy also oscillates, but is less in magnitude than the other energies. The x position versus time graph shows that the model is pretty accurate at predicting the x position, but the y position versus time graph shows that the model is not as accurate relative to the x position. Some potential sources of error are not accounting for other forces like drag, not accounting for other energies, and inconsistencies in marking the center of mass of the object during the tracker analysis. The energy principle is satisfied because the sum of the change in kinetic energy, the change in gravitational potential, and the change in spring potential is equal to 0, which is the total energy, so it is satisfied. And the reason why the total energy is 0 is because the spring potential energy is the opposite sign to the gravitational potential energy, and the kinetic energy has the same sign as the potential energy, but with a lot less magnitude. as we can see from the graph, and then from here from the equations. The average oscillation period in the X position was 1.614 seconds and 1.519 in the Y position, which is a difference of 0.95 seconds. The difference between the oscillations affects the calculation of the spring constant K, as we can see from the equation, the spring force, and the spring potential energy. And these differences could have been caused by drag forces, incorrect tracking of the center of mass, or even camera distortion.